Okay, perfect.
Looks good.
Yeah, so here are the list of wonderful co-organizers: Adam Clivens, Gabor Lugosi, Ankur Mitra, Prasad Raghavendra, Phil Schramm, and Yihong Wu. So in order to motivate sort of the setting for this program, I'll just give some sort of high-level motivation of the typical sort of statistics problem that we and sort of the rest of the world wants to solve. And so at the highest level, one wants to estimate a signal in random noise. And this sort of setting captures also learning a model, parameters of the model, given data, and so forth. Now, the sort of basic features of the setting are that the signal has some structure, maybe some combinatorial structure. It could be some graph structure. It could be sparse vector. It could be any of those things. And there are other features of the problem that describe the quality of the data. So it could be the amount of data, it could be the strength of the signal, and so forth. All right, so one wishes to solve some sort of estimation problem, in some specific context. And the two basic sorts of resources that one has in order to try to solve such a problem are, one, the data. Of course, this is what we have in front of us, from which we're trying to conclude an answer. And the second is computation. So anything that we're going to do on the data is going to require some amount of computation. And so if one wants to understand what's a good algorithm, what's an algorithm that's going to be effective, well, the first question would be, how much data do I need? And this question has been studied in mathematical statistics for a century.
Guy, we're only seeing the title slide. I don't know if you're advancing them.
I am. Oops. Well, let's see. Maybe there's a better way for me to share the screen.
We're seeing that.
So you're only seeing the title slide, is what you said, right?
No, we're seeing it.
I can share the desktop and then do this. How does that look?
That's it. We're seeing the.
Okay, good. So good. So perfect. So generic statistics problem: signal plus noise, or estimate parameters of a machine learning model. Basic resources: data and computation. So, like I said, mathematical statistics is concerned with how much data do we need, but it says nothing about computational complexity. At the same time, the field of computational complexity has been concerned with how much computation do I need to solve some problem, and says very little about the sorts of practical, real-life machine learning and statistics problems that we're faced with, because those problems have data that is benign in some sense. And most of computational complexity concerns worst case problems. Of course, with that said, I mean, there is, of course, the field of average case complexity, and also cryptography studies average case problems. But most of what's been done there doesn't apply to the sort of statistics problems that statisticians are faced with. Now, what's intriguing is that these two resources actually interplay one with another. And so these problems can't be studied only from one perspective. One actually needs to combine the two perspectives in some way. And so at the high level, that's what the aim of this program is to understand, how do these two resources interplay? How much of each of them do I need for each sort of problem that I'm interested in? So I'll give a sort of a case study here in this next slide. This case study is an example problem for which there is a pretty satisfactory understanding. And this understanding is captured by what can be called a feasibility diagram. And so on the vertical axis, we have a signal strength parameter. As we go up, the signal gets weaker. On the horizontal axis, there's a parameter capturing the sparsity of the signal. You can think of it generically as just something that's controlling the combinatorial structure of the signal that one wishes to recover. And over roughly a decade of intense study by many, many researchers, the following feasibility diagram has emerged. And what it does at the highest level is partitions the set of parameters of the problem into three regions. One, where the problem is just impossible, meaning it's impossible even with infinite computational power. There just isn't enough signal. The information is too weak. There's an easy regime where an efficient algorithm, often linear time or low order polynomial, can solve the problem. And then there's a hard regime where it's believed to be hard, and there's various forms of evidence indicating that it's computationally hard, but it is feasible in principle if one is willing to invest massive amounts of computational power. And so this problem is pretty well understood because there's this kind of demarcation of every possible parameter into one of the three regimes. And so this is a success of the field. But the concern is that this took a decade of work by a lot of people and dozens of papers on the topic. There are
1 minute.
many dozens of problems that exhibit this sort of behavior. And so this motivates the question, how in the world do we understand this landscape of problems? And how do we understand their computational feasibility as a function of how much data we have, or vice versa? How much data do we need for computationally efficient algorithms? The broad objectives of the field in a nutshell are: one, what is the amount of data that is needed by computationally efficient algorithms? Two, if we have notions of optimality that are supported by item one, then what are those optimal algorithms that achieve this minimum? More broadly, can we understand relationships between problems as opposed to studying problems in isolation, which is what's traditionally done in statistics? And can we elucidate relationships between classes of algorithms instead of just applying every possible algorithm to every statistical problem? We understand some hierarchy of their power. And so the program will bring together researchers from the disparate fields that study these questions: statistics, theoretical computer science, information theory, learning theory, statistical physics, to address these questions. And to that end, there are several workshops, each targeting one of these main objectives.